Welcome to Maths with EJD. In this video, we're talking about the Euler's method for initial value problems for ODEs. In the previous video, we had distinguished two types of problems. When we talk about ordinary differential equations, we talked about the initial value problems, and we also talked about the boundary value problems. So under the initial value problems, we identified two methods with which you can solve them, like the Euler method, and then we have the Ranjikuta methods. There are a couple of Ranjikuta methods, but the most popular one is the fourth order, which we'll be considering in the next video. Then for the BVPs, we also identified the finite difference method, finite difference method for solving boundary value problems. And we identified the shooting method. Okay, so in this video, we focus on the Euler method like that. So Euler method for initial value problems for ordinary differential equations. Okay, so Euler's method. Euler is one of those famous mathematicians that had input in several areas of mathematics. I remember when we were talking about graph and network theory, we had the idea about Eulerian circuits and all that. I suspect it's the same Euler all the way. So Euler's method is a numerical technique for solving first order. So it has to be first order. So beyond first order, it's not possible, right? For solving first order ordinary differential equations, That's what, so we call them ODEs of the form dy dx. So it's first order. So dy dx equals f of x comma y. So this is a set of ODEs with which that we use Euler's method to solve. So given an initial condition, say y of x naught equals y naught, Euler's method uses an iterative approach to approximate the solution at discrete points. Okay. So with that, let's talk about the formula for Euler's method. Formula. So the update formula. So we say call it update formula because after each process you need to do it again until you get all the iterations you need. So the update formula for Euler's method is yn plus 1 equals yn plus h f of xn comma yn. So this is the update formula for the Euler method. The interesting thing about this is that as simple as it is, I think it was very strategic. When we talk about the story of this black woman mathematician at NASA, I think this was what she used, to launch the first space mission or something close to that. I'm not quite sure of what that was now, but Euler's method was really useful. In fact, I think there's a movie in that in that line. So here where xn is the current value of x, xn is the current value of x, then you have yn, which is the current approximation. It is the current approximation of y of xn. Then we have h, which is the step size. H is the step size. So that tells us how we should increment the values of x. Then we have f of xn, yn. That is the function. This is the function defining, this is the function defining the differential equation, defining the differential equation. Okay. So we need to understand that Euler's method advances the solution by taking small steps h, using the derivative, at the current point, to estimate the next value. Okay, so having said that, let's look at an example that helps our understanding of the Euler's method. So imagine that you need to solve dy dx equals x plus y with y of 0 equals 1. That's the initial condition, using 0.1 increment, meaning that the step size is 0.1. So in that case, so let's talk about the solution. So given the differential equation, dy dx, which is equal to x plus y. Interestingly, this equation has, it actually has it has an analytical solution. It has a closed form solution. Okay, so we can easily compare whatever the numerics give us with the analytical solution. So with the initial condition, so this now with the initial condition, y of 0 equals 1. So we use Euler's method. With step size h equals 0.1 to approximate values of y. So generally speaking, we know that this is what the expression looks like, right? Yn plus 1 equals yn plus h of fx of n, y of n. So if you take it from there, see what the kind of thing we end up coming to. So if I take this now, so let's remind ourselves, let's talk about step-by-step calculation, step-by-step calculation going forward, step-by-step calculation. So again, the Euler's method is yn plus 1 equals yn plus h, the step size, times f of xn yn. Okay, so that means that f of x and yn in this case, this should be our f of x of y, right? So this is more like f of x comma y. Okay, that's our function right there. So we can use that to determine this, because we have just x plus y. So in that case, we can have yn plus 1. Okay, yn plus 1 equals yn plus h into x plus y, because our f of xn plus yn f of x and y is actually x plus y. So it means we have, in fact, better, it should be xn plus yn. That's what that looks like. So from there now we can say, so we can take the first iteration. So iteration one, so we say that at x equals 0. So the initial condition, right? Remember the initial condition is y of 0 equals 0. So y of 0 equals 1 rather implies that at x equals 0, then y is equal to 1. So that's like our initial condition. So meaning that x not equals 0 and x not equals 0 and y not equals 0. So those are the starting values for us. So in that case, now since we have x not, y not, we can then have, so it's more like n is 0. So this all imply that n is equal to 0. So if n is 0, so y, and y 0 plus 1 is 1. So y1 is equal to y naught plus h multiplied by x naught plus y naught. Okay. Uh, so that's what we have. And if that is the case, it means that y1 is simply going to be y naught is 1 plus h. Our h is 0 0.1, like we know already. So h is 0 0.1. H is equal to 0 0.1. So we just have 0 0.1 into x plus y. So x naught is 0, y naught is 1, like that. So that means that y1 is equal to 1 plus 0 0.1 into 1. So that means that y1 is equal to 1 plus 0 0.1 times 1 is simply 0 0.1. So that means that y1 is equal to 1.1. Okay? So corresponding to this, right? Corresponding to this will be x1. Of course, x1 is x naught plus h, x naught plus h. So in that case, we have x1 to be equal to x naught is 0, h is 0 0.1. So it means that x1 is going to be 0 0.1. Okay, so that's x1. So we already know x naught, y naught. Um, so x1 corresponds with this. So the next thing we are going to do, we can then go for the next iteration. That's first iteration, right? Should I have named it first iteration? I think it's better to name it first iteration. So let's say first iteration. Okay, first iteration. Let me do the fancy stuff. Yeah, first iteration. Okay, so let's go for the second iteration. I need something a bit darker. Say this. So second, oh, is that blue or black? Yeah, that's fine. Second iteration. So with second iteration now, we have x1 to be equal to 0 0.1 and y1, which we got at the other side, is 1.1. So those will be the value we get there is going to be carried over for the next iteration. Yeah, right. So y1 is 1.1. And don't forget, h doesn't change, it's 0 0.1. So with that now, we go ahead again. So now we need y2. So y2 now is going to be equal to y1. Y2 is going to be equal to y1 plus h into f of x1, y1, which is x1 plus y1, because that's the definition of the function itself. So if that is the case, y2 now is equal to 1.1 plus 0 0.1, plus 0.1 into x1. X1 now is 0 0.1 plus y1. Y1 is 1.1, like that. So we have y2 to be equal to 1.1 plus 0 0.1 into 0 0.1 plus 1.1, that's 1.2. So that's 1.2, like that. So that means that y2 is equal to 1.1 plus 0 0.1 times 1.2 is actually, I think 0 0.12, right? Yeah, that should be 0. So we move one decimal place forward. So that's 0 0.12. So we have y2 to be equal to 1.1 plus 0 0.12 is 1.22. And this is our y2 now, okay? Our y2 is 1.22. So with y2 being 1.22, so what is the next x2? So the next x2 is simply just going to be x1 plus h. Okay. So that is the x1 that we brought up to this point is 0 0.1. 0 0.1 plus h is also 0 0.1. So x2 now is equal to 0 0.2. So we need this for the next level of iteration. So let's go for the third iteration. Third iteration. So for the third iteration, we need y3, right? So we know that, of course, we need y3. So y3 is equal to y2 plus h into x2 plus y2. And if you don't forget, x2 now, I guess I just want to make it different. X2 now is 0 0.2. X2 is 0 0.2. Y2, we just got that from the second iteration. That's 1.22. 1.22. H doesn't change. That's 0 0.1. So we move on to the third iteration. Y3 is equal to, so Y3 is equal to Y2, that's 1.22 plus H 0 0.1 into X2 0 0.2 plus Y2 1.22. So Y3 now is equal to 1.22 plus 0 0.1 into 0 0.2 plus 1.22. That's 1.42, I believe. That's 1.42. So y3 is equal to 1.22 plus 0 0.1 times 1.42 is 0 0.142. So if we add all that, so y3 now is going to be 1.364. So y3 is 1.364. So that is y3, 1.364. Again, we have the corresponding x3, which is going to be x2 plus h. The x2 we brought here is actually 0 0.2. So x3 is 0 0.2 plus 0 0.1, which is h. So x3 is equal to 0 0.3. So we have this. So that takes us to the fourth iteration. That takes us to the fourth iteration. Let's say this is what we want to use. So we have the fourth iteration now. So we can go on as much as we want. So fourth iteration, again, we need y4, which is equal to y3 plus h into x3 plus y3, h into x3 plus y3. And right now, we have x3 to be 0 0.3. Y3 is what we just obtained up there. That is 1.364. Oh, is it 1.364? It should be 1.362, sorry. 1.362. 1.362. So that little error, of course, it may not, you may still keep going, but then that little error is going to show a little bit. So that's 1.362, not 1.364. 1.362. H doesn't change, it's 0 0.1, it's the step size. So that 1.362 now, that we go ahead and have y4 equals 1.362 plus 0 0.1, 0 0.1, 0 0.1 into x3, which is 0 0.3 plus 1.362. Okay, so y4 is equal to 1.362 plus 0 0.1 into 0 0.3 plus 1 point, that's 1.662, I believe. That's 1.662. So that y4 is equal to 1.362 plus 0 0.1662. 0 0.1662. So that y4 now is equal to 1. Okay, we have to be careful here. Okay, we can set it up. This is 1.362, 0 0.1662. So 282, 1.4282. Is it 4? It should be 5, right? 2 should be 1.282. Yeah, 1.5282. So that's 1.5282 for that side. So this is 1.52, 1.52, 1.5282. Okay. And this, of course, corresponds with x4, which is equal to x3 plus h. So x4 is 0 0.3, 0 0.3 plus 0 0.1. So x4 is equal to 0 0.4. So we can keep going, right? But I mean, we can keep going, but let's stop here and go to Python later. So right now we can have the let me go for this. So we can have the computed values since we have them listed, computed values. Okay. So just like I like to do, so we can have I. Okay, we have I goes from 0 to 4 in our case. Then we have xi, we have yi, the results. Okay. So we have 0, 1, 2, 3, and 4. And 4, right? So this is xi, that's x naught. So our x naught is 0 where we started. So I can populate this with this. X naught is 0, y naught was 1. But when we did the first iteration, x1, y1, x1 was 0 0.1, y1 1.1. So we have 0 0.1. So we can say this is 0 0.0. So this is 1. This is 0 0.1 and this is 1.1. Then next we have what now? This is next one, of course, these ones are easy. Just increment by 0 0.1 each. Then we just have the corresponding values. So because, I mean, the last result is 1.5282, 4 decimal places. So we have 1.52, 1.5282, 1.52, 1.5282. Okay, I guess I want to make it this to make it easier for me. 1.5282. Okay, so I'll just make it 4 decimal places. What is y3? Y3 is 1.3620. 1.3620. Then y2, y2 is 1.2200. 1.2200. I mean, just the decimal place is just for consistency. 1.2200. So I can go back to the ones I had done before. This is 1.1, right? So we have 1.1000. And the first one, we can just write that as 1.0000. So that's the table for our iterations. So before I go for the Okay, well, I guess I want to go and come back. Let's look at the Python implementation of this. Let's see what that looks like. So if you look at the Python implementation, so let's see what it looks like. So you define, you just in line 5 and 6, you define the function that which you have to return x plus y. So whatever you want to solve in your own case, you can put it there. Then now we have the exact solution. If you check in the previous case, right, we already had the exact solution to be 2 raised to power uh 2 raised to power x. I think 2e raised to power x or something like that. I think uh that's the numerical, the exact solution, right? 2e raised to power x minus 1. That was the exact solution. So because we want to compare, we want to compute error for each step, and that's why that is necessary. So then for the Euler's method of implementation, so all of that is defined in lines 13, I think, even up to 22. So you have the y values, you have the x values, and the how the values will go, how to generate them, starting from x naught and incrementing by h and all that. Then you have the y values, of which takes the values of x to become y. And then, of course, you have the initial condition in line 25, x naught, y naught, that's 0, comma 1. You have the step size 0 0.1. So you can play with this a lot. I mean, put any function you want to put. If you know the exact solution, so you can define it differently based on whatever it is. So with all of this, you can run this and then it spews out the result. So you can say our result from, so we're able to do the first 4 iterations. And you can see our results are consistent. So the Euler approximation, you have one. So you can see you have one, we have 1.1, 1.22, we have 1.362, we have 1.528. So now imagine if you want to do all these plenty iterations, that's up to like, I think that's like 10 of 20 iterations or so. But with Python code, it can keep going like that, it can keep going and going and going. So if you want it to go, let me see, this is here now we took x to be 2. What if we took x to be, say, 5? So we are going to have many more iterations. So the iterations are way longer now, up to 5. So, and then now you see the graph now. The blue is the exact solution. The graph the exact solution gives you, and the Euler approximation is the red one. So you can see from 0 up to like 2.5, the results are exactly the same, but by 3 it begins to deviate. Yeah, like that. But I mean that's to tell you that Euler solution is somewhat consistent. What if we say xn is 50? That's a lot. Okay, so you can see it's so plenty, and then okay, the deviation starts. So the deviation becomes very large at some point. So let's return it to the 2 we started working with. So you can copy out this code, put it in your whatever in your environment, and play with it. Yeah, you won't get it on YouTube, but you get it on Facebook. If you follow me on Facebook, you can copy this code from there and then just try to run it. So this is how the Euler implementation looks like. So you can do more iterations faster instead of having to do it manually like I did in the other situation. Okay, so that is that. Um, okay, so I'll be thinking of a practice question. Uh, so let's go back. So we've seen how the iteration goes. It's really interesting. The formula is simple. You just keep implementing it. Now, to before we even do anything, before I give the uh s- the practice question, right? Let's look at some issues surrounding accuracy and limitations. Accuracy and limitations, talking about the Euler's method, accuracy and limitations. So we see that Euler's method, Euler's method provides a simple way, provides a simple way to approximate solutions, to approximate solutions, but it has limitations. But it has limitations. That's why other methods are used. That's why Ranjikuta, for instance, is very helpful. So let's look at some of these limitations. The first thing is about accuracy. So you see that accuracy depends on the step size h. So if you want high accuracy, you take smaller h. Okay, I guess I can just say that with my mouth. So accuracy depends on the step size h. So a smaller h leads to better accuracy, but increases computational cost. So if you imagine that the step size I was using is not 0.1, that it is 0.01. So before I do from 0 to 1, that'll be like 10 iterations already. So you get more accurate results when h is smaller, but the computation is more tasking. Like it takes more computational cost. Then the next thing is about the global truncation error. The global truncation error is big OH. What that means is that errors accumulate with each step. So each step you take, you see that errors accumulate. And that is why if you remember the Python code, right? The more I increase the number or the terminal value, that the more I increase where we should stop, the more the graph departs from, the more the Euler approximation departs from the exact solution. Okay, so errors accumulate with each step, right? Then the next thing is that it is not suitable. It is not. It is not suitable. Okay, it is not. So Euler's method is not suitable for stiff equations. For stiff equations. So there's this idea of stiffness in numerical analysis. So that means for rapidly changing functions, for functions that change very rapidly, Euler's method may require an impractically small step size. Okay. So if you have equations that change so fast that it just blows up within a very short time, so Euler's method may not be the best for that. So that takes us to the next video, right? Which you want to look forward to. So to improve accuracy, to improve accuracy, higher order methods, higher order, no, Euler is just for first order. So higher order methods, um, like the Runge-Kutta method, which we are going to see in the next video, like the Runge-Kutta method, are often preferred, are often preferred. Okay, so um, and we've seen the Python code already, which shows us how that when in the beginning the results are about the same. The Euler predict approximations are about the same with the exact solution, but as the steps increase, you have deviations from that. Okay, so let's look at some practice question. I guess I have a lot. Let's see how much I can do here as far as practice questions are concerned. Practice question. Okay. Let me go darker. Say this. So use okay, let's see. Talking about basic application, right? Question one. Use Euler's method with step size. Step size h equals 0.2 to approximate y of 0.4. So that's like second iteration or third iteration that maybe, yeah, 0.2, right? So if you start from 0, 0.2, 0.5, that's like third iteration. So approximate y of 0.4, okay, for the initial value problem, dy dx equals x squared plus y. The initial condition y of 0 equals 1. So what we did before was x plus y, not x squared plus y. So that's 1. Can we look at a second one? Solve dy dx equals x plus y squared. Now x plus y squared, not no longer x squared plus y, with y of 0 equals 1 using Euler's method. With h equals 0.1 to estimate y of 0.3. So that means 0, 0.1, 0.2, 0.3. That's like you do it up to the fourth iteration. That's what that implies. You know, that's that. So let's take another one. Have a lot. Let's keep going. I think it's interesting. So you have a lot to try your hands on. So we can use Runge-Kutta for this too. When we do Runge-Kutta, I'll just zoom back here. So number 3, okay. Still, yeah, okay, that's done. Imagine, consider, consider, um, the differential equation. Consider the differential equation. Consider the differential equation. The x, dy dx equals 2x minus y, and y of 0 is equal to 1. So consider that, right? Um, find the exact solution. Find the exact solution and compare the results with Euler's approximations, Okay. Then let's look at another one. I guess this is the first time I'm giving uh this many assignments. That's question 3 right there. Question 4. Well, I think this is helpful for Ranjikuta too. So question 4, given the y dx equals e raised power x minus y with initial condition y of 0 equals to apply apply Euler's method. Apply Euler's method with h equals 0.1 to approximate y of 0.3, then compute the percentage error. We talked about error when we started out. Compute the percentage error. So if you don't know percentage error, you can check my second or third video, I think, under numerical analysis. Then compute the percentage error if the exact solution is, so exact solution to that, if it is y equals e raised power x plus 1, that's the exact solution. And lastly, I have another one. Let me use a marker I've not used so far. Okay, let me go for this. So question 5 now, I think. Question 5. Lovely questions here. So approximate y of 1 using Euler's method, with h equals 0.2 for the equation. H equals 0.2. For the equation dy dx equals 3x plus 2y. Initial condition y of 0 equals 0. Okay. Yeah, so that goes. So you have 5 questions to try your hands on. Okay. So feel free, let me see in the comment section your answers. Then you can get the Python code on Facebook, so you can also use Python to try some of this out. All right, that would be so lovely to see you understand, to try manually and to use Python to solve these problems. So let me see that in the comment section. Let me know how helpful these videos are. Also, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. So watch out for the Ranjikuta method video after now. Bye.